So in the previous video of this season, we noted that there was a connection between the integrals of Calculus 2 and the derivatives of Calculus 1. And in my opinion, that's not at all obvious that there is a connection between those two ideas. The derivative, which is this rate of change, which is this slope of a tangent line, and then the integral, which represents this cumulative total, this adding together tiny bits of things, this integral, which represents the area, the net area under a curve. We found yesterday that there's actually a very sneaky connection between those two ideas, that in some sense the derivative and the integral were opposites of each other, that if you took an integral and then you took a derivative, then they kind of canceled each other out. Today we are going to talk a little bit about how to use this idea of integrals and derivatives canceling each other out and being opposites to calculate integrals more quickly in certain situations. And to give you an example of a situation where we may want to have an additional tool in our toolbox to help us with integrals, suppose that I gave us a problem like this one, the integral from 1 to 3 of t squared dt. I look at this problem, there's no symmetry that I can use to make this problem easier. If I try and graph this function, there's no geometry that I can use to get the net area exactly. So in a situation like this one, I would be forced at this moment to use like a Riemann sum estimate. But a Riemann sum estimate is not permitted because a Riemann sum estimate is not exact. If you see that keyword exact, then exact means estimates are not allowed. So if your only option is a Riemann sum estimate, but estimates are not allowed, then you need additional option. You need new ways to solve problems like this one. And that's what the fundamental theorem of calculus is going to give us. Now, I've debated whether or not I wanted to take the time to explain exactly why the fundamental theorem of calculus works. And I have decided that I am not going to take the time to do that. I don't think that that is effective use of the very limited time that I have with you guys in this class. So instead, what I'm going to do is I'm just going to state the fundamental theorem of calculus. And then if you are curious why this theorem works, I will find some other video that explains where this theorem comes from and exactly why it is true. So, the fundamental theorem of calculus. You are in a scenario like this one, where you're integrating a function from a to b. And you're in a scenario where geometry is not going to work, symmetry is not going to work, but you're not allowed to get an estimate using a Riemann sum, or maybe you just do not want to estimate the answer using a Riemann sum, because Riemann sums can take a bit of time. In that situation, there is another method that can be used to calculate the value of this integral. You can calculate the value of this integral by just plugging a and b into some other function called capital F and then subtracting those two outputs. And the only requirement on this function capital F is that capital F has to be a function whose derivative is equal to f of x. This function lowercase f in your integral is what's equal to the derivative of f. In other words, this function capital F is the derivative backwards, the opposite of the derivative. We were talking yesterday, integrals and derivatives are kind of opposites of each other. If you do one and then the other, they cancel each other out, so they're kind of opposites. And this theorem is calling on that idea. This function, capital F, is the opposite of a derivative of lowercase f in your integrand. Let me demonstrate to you how I would use this fundamental theorem of calculus to calculate integrals in a situation where geometry or symmetry cannot be used. Example number 1. Someone asks me for the integral from 2 to 4 of x cubed dx. Symmetry cannot be used here, and geometry cannot be used here. So what shall I do to find the exact value? The exact value, no estimates are allowed for this integral. The first thing that I'm going to do, step 1, is I'm going to find a function. I'm going to come up with any function whose derivative is this guy that I'm integrating. I'm going to find any function whose derivative is equal to x cubed. So can you think of any function where when you take the derivative, the result is equal to x cubed? Well, maybe you remember that when you take a derivative of a function of the form x to some power, that the derivative causes the power to decrease, right? So if I want to be able to decrease the power, and then after the power has decreased, there's a 3 up there, what power has to be up here in the beginning in order to get 3 in the end? Well, if I have an x to the 4th at the start, and then I take the derivative of x to the 4th, then the power will decrease from 4 down to 3. So that's off to a good start. If I have an x to the 4th here, and I take the derivative, I have an x to the 3 in there. Unfortunately, this is not quite right now, right? If I take the derivative of x to the 4th, what results from that is technically 4 times x to the 4th. So do you have any ideas about how I could fix this function so that its derivative is exactly equal to x to the 3rd power? Well, one option is to try putting a constant multiple on this capital F of x, and to try something like 1/4 x to the 4th power. Now, if I take the derivative of this, then the 4 comes down to the front, cancels the 1/4, so I have just a 1 out there in the front, and then the power of 4 decreases to 3, and so that's an exact match to the x cubed that I have in this integral. So here is a function whose derivative is x cubed. Capital F of x equals 1/4 x to the 4th power. Step number 2, using the fundamental theorem of calculus to calculate this value. Step number 2 is to plug our two limits of integration, b and a, into the function capital F that we just wrote down. In our situation, our lower limit would be 2, and our upper limit would be 4. So we would be plugging those values, 2 and 4, into this function. So f evaluated at 4 would be 1/4 4 to the power 4, which is 64 units, if I have that right. F evaluated at 2 would be 1/4 2 to the power 4. So that would be 4 units if I remember correctly. So this would be F evaluated at our upper limit and F evaluated at our lower limit. And then finally, the only thing that's left to do here, step number 3, is subtract the values from step 2. Specifically, subtract them in the order of upper limit 4 minus lower limit 2, in our case 64, minus 4, in our case 60 units. 60 would be the exact perfect totally accurate value of the integral from 2 to 4 of x to the third power. Now let's take a minute graphically to confirm that this answer makes sense. So here is a graph of the function x cubed between x equals 2 and x equals 4, and shaded in red is the area underneath that curve. And here in the picture, each of these blocks is 1 unit wide and 10 units tall. So the area of each block is 10 units. And so we can see that there's approximately 3 full blocks. Here's almost another full block here, 4 blocks. And then maybe another, another block here, and then another block maybe between these two. So just by counting blocks, we can see that we have about 6 blocks underneath this net area, about 6 blocks, each of area 10 squared units. So I would estimate a net area of approximately 60 units just by eyeballing this graph as well. What we have found using the fundamental theorem of calculus is not only is the net area approximately 60 units, the net area is exactly 60 units. And we have found that using this 3-step process in the fundamental theorem of calculus. Let's try it again. Someone says, let's find the exact value of this integral, the integral from 0 to pi over 2 of cosine of x dx. So step number 1, I have to find a function which we call capital F of x, and that function has to satisfy the property that if you take the derivative of capital F, the result of that derivative is going to be equal to cosine. So what do you think? Can you think of any function where if you take its derivative, the result of that derivative is cosine? You may remember from Calculus 1 that cosine and sine were very strongly connected. If you took the derivative of sine, then the result of that was cosine. And if you took the derivative of cosine, the result of that was negative sine. So sine of x is the function that we're looking for. This is the function whose derivative is cosine of x. Now the next thing that we need to do is go ahead and plug our limits into this function. And so from that process, we have f evaluated at our upper limit, pi over 2, and sine evaluated at pi over 2 is equal to exactly 1 unit by the unit circle. F with 0 plugged in, sine of 0 is exactly 0 by the unit circle. And then the last thing that we have to do, step number 3, is subtract. So upper limit minus lower limit, that order. 1 minus 0 in that order. Result 1 is the net area under the graph of cosine, according to this fundamental theorem formula. Let's have a look at the graph of cosine, and let's check to see if this answer makes sense. Here, shaded in red, is the area under the graph of cosine between 0 and pi over 2 units. And each one of the squares in this picture is 1 by 1. So each one of the squares in this picture has an area of approximately of 1 squared unit. And we can see that if we combine this red area here with this little wing portion on the right side that sort of fills in this gap, yeah, we would expect the net area to be approximately 1 square or 1 unit. What is surprising, what is extremely surprising, is that that net area is equal to exactly exactly 1 unit, not 9.98, not 1.03. The net area is precisely 1 unit under that curve. Kind of amazing. Now, the fundamental theorem is so beautiful and so much nicer than the methods that we've seen up to this point that students have a tendency to kind of fall in love with the fundamental theorem of calculus and apply it to all of our problems. But I do want to make sure that you are aware of, in my opinion, the one serious major drawback of the fundamental theorem of calculus, and the reason why we cannot use the fundamental theorem in all situations. The major pros of the fundamental theorem of calculus is that when you can use the fundamental theorem, it's generally easy and it's generally very fast and it's generally very accurate. In fact, it's exact, which means it's perfectly accurate and there's no error whatsoever. But all of this comes with a big sort of asterisks attached to it that easy, fast, and accurate only apply when the FTC, the fundamental theorem of calculus, can actually be used. The major drawback of the fundamental theorem, and the reason why we cannot use it every single time, is step number one of this process can be very, very difficult. Someone says find a function f of x whose derivative is this guy in the center. That's a very difficult process sometimes. It's not even always possible. Now, throughout the next season, we are going to be learning a lot of different techniques to help us to find f of x in a variety of situations, to help us to find f of x quickly and easily. However, even by the time we get to the end of this class, there will still be many, many, many situations where you cannot find this function f of x, and therefore you cannot use the fundamental theorem. So bear that in mind. This is a beautiful tool, but it cannot be used in every situation, and that's because of this drawback right here. Step number one can be very difficult sometimes, and we will explore that in the next couple of episodes. Editing Sam here. In a rare twist, I decided I actually had time today to cover a little bit more than what I had originally planned. So, what I would like to talk to you about in preparation for season 4 is this language of an antiderivative. This function capital F of x that shows up and that we find in step 1 of the fundamental theorem is given a special name, and it is called an antiderivative of lowercase f of x. So diagrammatically, the relationship between capital F of x and lowercase f of x is that if capital F becomes lowercase f when you take a derivative, then lowercase f becomes capital F if you take an antiderivative. So the antiderivative, as the name suggests, is literally just the opposite or the reverse of the derivative in the opposite direction. That is what we call an antiderivative. For example, if I were to practice using this terminology, I would say that 1/4 x to the fourth is an antiderivative of x cubed. And I would say that sine of x is an antiderivative of cosine. Now, it's possible for a function to have more than one antiderivatives. Actually, it is common, it is typical for a function to have several, infinitely many antiderivatives. For example, If I have sine of x, we know that sine of x is an antiderivative of cosine. We know this because if we take the derivative of sine of x, the result is equal to cosine. However, I could also say that sine of x plus 2 is an antiderivative of cosine. Why? Because if I take the derivative of sine of x plus 2, then the derivative of sine becomes cosine, the derivative of 2 just vanishes, and the result is equal to cosine once again. The same thing would be true of sine of x minus 7. The same thing would be true of sine of x plus pi on the outside. The same thing would be true for sine of x minus 214. No matter what number we add or subtract to this function, it doesn't matter, because when we take the derivative, that constant will go to 0, and we will still get back the function cosine. Now, this pattern holds true not just for cosine, but for any function where we're talking about its antiderivatives. For example, someone says, what is the format of every antiderivative of the function x squared? I can say, well, one antiderivative that I can think of right away for the function x squared, a function that would become x squared when I take the derivative. If I want to get an x to the power 2 out of power rule, I should probably start with an x to the power 3, so that when that 3 decreases by 1 unit, it becomes 2. And if I want to get x squared exactly, I should probably have a 1/3 in that expression as well, so that when power rule causes this 3 to come down to the front, that 3 in the front kills this 1/3, and then I'm left with just one copy of x squared. So 1/3 x to the third power would be one antiderivative of this function x squared. But as we just observed, 1/3 x to the third power plus 4 would be another antiderivative. 1/3 x to the third power plus, 17 would be another. 1/3 x to the third power minus 10 would be another, and so on and so forth. No matter what constant, no matter what number I added out here to the side, the added constant doesn't matter, because when I take the derivative of that constant, it vanishes, and I will still end up with x to the second. In general, if I were to write down the general format of all the antiderivatives of this function, I would write down 1/3 x to the third power plus c, where c here is standing in for whatever constant you want. It doesn't matter what the constant is. No matter what constant you add here in the back, the derivative of this expression will still become x squared. So this expression represents all possible antiderivatives of this function, one antiderivative for every possible value of c. As we go into season 4 is all about learning the rules and processes to come up with the antiderivatives of functions very quickly, so that we can apply fundamental theorem of calculus easily in a lot of different situations. And this plus c is something that you will be seeing very, very often in that season.